Hello, welcome to part 2 of using the golden ratio to predict the prime density. Here's the formula for that. So yeah, if you're ever going to use the golden ratio, obviously the Fibonacci sequence comes into effect. So yeah, let's have a look at that. So here's some Fibonacci numbers, and here's the formula you use. So the amount of primes less than n Fibonacci number squared is equal to the amount of primes less than the next Fibonacci number times that the Fibonacci less than that divided by 2. So here's an example. If we take the 22nd Fibonacci number and square it, this is how many primes there are. If we take the next Fibonacci number and the amount of primes less than that one and times it by the Fibonacci number less than that, these two numbers, you get that number, which as you can see is very close. And we'll use another example down here. So the amount of the number of primes less than this Fibonacci number squared is equal to the amount of primes less than this Fibonacci number times this Fibonacci number will give you that, and there's the real answer. Okay, so you can use that formula to use it. But as you can see, the numbers are getting higher and higher again, and that's why we combine this with ln minus 1. So here I've isolated the n on the one side, and now we've got a bunch of square roots. So I'll explain this formula. To find the number of primes less than n, you find the square root, so that would be this line down here. You divide that line by the golden ratio to get you this line segment here. You times that by ln minus 1 of the amount of primes less than that, right here. You divide it by 2 to get you your area of this triangle. You find the area of that triangle, and that's how many primes are less than this n. And here are some examples for you. So if we make n this value, ln minus 1 gives you that. If you add the golden ratio, it bumps it up to that, and there's the real answer. Here's a higher example for you. As you can see, it's actually getting better and better as we go. Now, the next logical question is going to be, will it ever pass the amount of primes less than n? And yeah, it does. It happens around here at these values. Yeah, as you can see, it's almost exact at this much. And then we get to here, it's definitely, oh, it is over here, actually, never mind. So it does go over, but yeah, it goes over very slowly. As you can see, if we more than double that number, it's still barely over. It's 0.9996 away. Still closer than ln minus 1. If we double that number, you can see it's moving away, but very little. And this is as high as I can check. So if anyone knows how to check higher values of how many primes are less than a certain number, please let me know. So yeah, at first when I saw that it passed, I was obviously very disappointed, because that to me implies that it's going to just the gap's going to get bigger and bigger, and it's going to be meaningless. But then I pondered it for a while, and it made me realize that there's 3 options to this. Well, 3 outcomes. Either it's going to come back down, which would be incredible. That would definitely show an underlying connection between E and the golden ratio. Or 2, it can become an upper bound. Or 3, this is all just a very, very odd coincidence. And I'll show you some details on all those points right now. So let's go to the calculator so I can show you a few things. So let's just zoom in here. So here we have the golden ratio up top. Then we have the formula. Then we have x over ln x minus 1. Then we have just some random value of x here, and then we have a divided by b and b divided by a. So these two divided by each other, so I can show you the difference between them. And this last section I'll show you later. So yeah, as you can see, they're very close. And so now if this is an upper bound, it's not that big of a difference. And that's a very thin line, which I'll show you in the graphing calculator. Yeah, and if you change any of these parameters, that percentage gets a lot worse. So you see that 998. If we just add 0.1 to the golden ratio, 0.995, it gets worse. If we minus 0.1, minus 0.1, you can see 991. So yeah, the golden ratio has to be perfect for this to work, or it doesn't work. You can change any of these parameters and it doesn't work. So as for it being an upper bound, if we just add as many numbers as you want here, I've gotten up to the 300, 10 to the 300, and then the calculator doesn't work anymore. Yeah, these two things, numbers barely change. And yeah, you can go on forever and ever and ever. As you can see, the percentage is getting closer when you divide them, and you get the idea. I don't know when you want me to stop here. Let's stop here. So at 110 zeros, you can see they're still very similar. So I'll show you in the graphing calculator how close they actually are. As for my first point, that it may come back down eventually. Well, the golden ratio has some very interesting properties in that it does stuff like that. If you raise the golden ratio to a whole number, the higher the number gets, the closer to a whole number you get over here. Not only that, it rotates between being just under a whole number and over a whole number. So at 10, it's just under a whole number. At 11, it's just over. At 12, it's just under, and that repeats forever. Also with the Fibonacci sequence, if the higher you go up, you divide that Fibonacci number by the Fibonacci number after it or before it, that also rotates between being just below the golden ratio and just above the golden ratio. So let me show you this on a graphing calculator here. Give me a second. So yeah, here are the two formulas on a graphing calculator. You can barely tell them apart. You have to really zoom in. Okay, and this goes on forever. I don't know how high you want me to go here, but let's just go higher so I can change some of the parameters for you to see what happens. Okay, so there we go. We're up in the 38,000s. Let's go further than that. Okay, so there you go. We're around 59,000. So there's the space. So let's just change some parameters here for you. Okay, so let's just add 0.1 to the golden ratio everywhere. And as you can see, the line, they're not even close anymore. Okay, so let's minus the 0.1 from the golden ratio. Sorry. Minus and minus. You can see they're not as close. They're obviously close proportionally, but not nearly as close as if you use the golden ratio perfectly. Now, once again, you can change any parameter you want, and it's going to get worse. As for that thing about adding +1 or minus here, I'll show you what that does, actually. So if we just add +1 to the golden ratio down here, we'll zoom out, you actually get the golden ratio there from ln minus 1. If we minus 1, the golden ratio appears that way. Okay. So yeah, you can play around with this all you want, and no matter how you change it, it's never going to be as good if you use the golden ratio. So yeah, if it's an upper bound, it's a great upper bound. It almost says to me that by using the golden ratio, you are making lines as parallel as possible without being parallel. Whether this is a deep connection between E and the golden ratio, I'm still not sure. But at the very least, it looks like it may just be a great use of the golden ratio, and that you can use it to make little tweaks to anything you want. And it works amazingly for a very long time. And no other number seems to have this amazing property. All right, thanks for watching. And if you have any ideas for me, please let me know. I'm no mathematician, and I would love help exploring this as much as possible. Thank you very much.